so my first question, what I want to know about the DC machine. So anyone tell me what about DC machine, just simple way. Before we discuss about the DC shunt motor, I just want to know about the DC machine. Anyone? Okay, no problem. So here DC machine, actually my writing not good in this. So DC machine in two parts. First one is DC motor. Okay, DC motor, and second one DC generator. Okay, so what is difference between both DC motor and DC generator? Anyone? So here I am getting the input from the electrical quantity in DC motor. Okay, in DC shunt motor, the input from the mechanical quantity. So just input is electrical in DC motor, electrical to mechanical, electrical to mechanical. In input is electrical and output get mechanical. Okay. For an example, I am getting electricity and on the switch on and getting the fan on. So that is fan outcome is mechanical and getting the input supply. Okay. So DC machine is the electrical quantity in input terminal and get the output from the mechanical. In DC generator, it is mechanical in input and getting output from electrical. Okay, so it is the difference. So this is the difference between sorry, DC motor and DC generator. So in DC motor basically in circuit form it is divided into three parts. Okay, so first one is separately excited most. Actually, before we discuss about the motor, I'm just in DC motor, in DC machine, I am just basic term. When we design the DC machine in terms of DC motor or either DC generator, I have come into the picture two parts, make two binding. First one is armature binding and second one is field binding. Okay, first one is armature binding or second one is field winding. Okay, so in though two winding are used when we design the DC machine. Okay, either you have to design the DC motor or you have to design the DC machine. So you have used the two winding, armature winding and field winding. Field winding, okay, I'm discuss in upcoming slides what is the armature winding and field winding. So before we coming back, DC motor divided into three parts in circuit form. First one is separately excited. Okay, separately excited, and second one is self excited. Self excited into divided into two parts. So self excited. First one is separately excited and second one is self excited. Okay. So separately excited means armature binding and field binding are separated. Okay. But in self excited divided into two parts. First one is DC shunt motor. DC shunt motor. Okay. and second one is DC series motor. Fine. Okay, so DC motor divided basically two parts, separately excited means two winding are separately, armature winding and field winding. When we design the separately excited DC motor, and self excited divided into two parts, DC shunt motor and DC series motor. In DC shunt motor, I am discuss about the DC shunt motor here, because when we actually my experiment DC speed control of DC by DC shunt motor. So DC shunt motor. So I am here in brief discussion about the DC shunt motor, but you know about the DC series motor also. So in DC series motor, I have used two winding, armature winding and field winding in series connection. Okay, in DC series winding. But in DC shunt motor, I have used the winding, armature winding and field winding in the parallel. Okay, fine. Is it clear? Anyone responds me?
Yes, sir.
Okay. So today I am only discuss about the DC shunt motor. Okay. So DC shunt motor looking like this. Uh, this one. This is the circuit. So here you can see here the in DC motor means input from the electrical. So this is the terminal plus and minus. Whoever who uh, which student in physical mode perform the DC shunt motor, speed control of DC shunt motor, you have already seen that input from the electrical supply. So this is the plus and minus. You can see in the lab, you can see this is notation in the physical mode, L and double L. Okay, remember? Anyone who have to perform the this experiment in the physical mode? So you have understood easily. This is the input supply. So mentioned in the lab, L and double L. So this is the input supply. It is called a VL. So total voltage. Okay, and getting the line current from the goes to two winding. Actually, I am using the DC shunt motor, so it is connected to both winding. This winding is field winding, or this one is armature winding. Okay, so both winding have a internal resistance. So in armature winding, I am showing here in the external resistance means armature resistance. That is notation of RA. In the field winding, you have to see here the RF is the field resistance. Actually, when we use the winding, I'm say actually coil are used, then RF and XF means inductance also there, because but anyone know about the how I actually मैं इसको actually I want to sorry actually RF and XL I am not mentioned here XL. Why I am not mentioning here XL? Why? Because when you are used to binding, RF and XL are also there. Why we are not used here? Anyone? बताओ भाई. Because we are using we are studying here the DC shunt motor. So DC supply is a frequency is zero na, huh? When frequency is zero, XL is in terms of inductance 2 pi FL. F means frequency is zero, XL is zero. Okay, reactance is here is zero. So I am only mention here in terms of resistance only. Fine. Okay. So I am using the field winding, and so this is called the field winding. This one called the field winding. Okay, so this one is the armature winding. Okay, armature winding. Okay, so when we design the DC machine, actually in machine also either about the DC machine or AC machine, which is two stator and rotor are there. Stator, which is the stationary part, are place the binding, and rotor also place the binding, which is rotating part. So I am using only two in the machine, stator or rotor. Stator means stationary part and rotor means rotating part. So in the DC machine, stator placed on the field winding are placed on the stator, because I am using here field winding as a constant. Okay, so I am here when we design the DC machine, field winding are placed on the stator. Okay, or in moving part means rotate armature winding is the rotating part, so I am place this winding on the rotor. Okay, so in the DC machine you have to understand rotating, or which one is rotating, armature. So I am placing on the rotator winding, rotor part, and in stator I am place the field winding. Okay, so one point is clear. Okay, so when we use the rotating quantity when you 12th you have to study na Faraday law. What is the Faraday law? Anyone? बताओ भाई, Faraday law. Anyone? बोलो भाई, आवाज नहीं आ रही. बताओ आयुष. Hello, am I audible? Hello. 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 Am I audible or not?
Yes, sir, you are audible.
So you have to answer na. What is the Faraday law? Anyone? Response me. No. If you know, then tell me.
So the change in flux associated with the coil changes, then EMF is induced in the circuits.
Yeah, exactly. Okay, good. So, one second. So screen is visual na?
Yes, sir.
Yes.
Okay. So my any moving part come into the picture, EMF will induced, cut in the flux, and d phi by dt equal to d phi by dt. Okay, rate of change of flux will produce the induced EMF. This is now Faraday law. Response me here is very okay na. So here the moving part, which one? Armature winding na. So armature winding produce the EMF is mentioned notation is EB. EB means back EMF, because back EMF is called the induced EMF. Okay, so I am here connected with brushes because this is the moving part na. So I have connected with directly, so circuit will destroy. Actually this one is moving part. Okay, so electrical part, if actually brushes are stationary, I am holding the armature winding. Okay, so this is the moving part. When we moved, so stator, sorry, hold the armature winding by the brushes. So I have mentioned this is brushes, which is voltage drop BB. Okay, so here the circuit of armature winding, actually this is the armature winding. So I have for clear understanding, I have connected with armature resistance. So you have to apply the KVL and KCL in easy way. So I have just mentioned here, but actually this is the armature winding. Okay, so this one is a field winding. So field winding is produce the flux is a constant part, because field winding are placed on the stator, and moving part are placed on the rotor. Okay, so moving part, which one? Armature winding. Clear? Clear or not? Please, yeah, response me, then I follow.
Yes, sir.
Okay, so BL is the total voltage. Which one? Input. Okay, which input? Electrical or mechanical? Please response, I have told you. BL is an input or electrical input? Okay na? Okay, or RF is the shunt field resistance. Why we called the shunt field? Because the shunt winding. Okay, shunt winding. So I am notation for shunt field winding. Oh, armature, RA is the armature resistance. This one RA is the armature resistance. IL is the total current from the terminal input, and IF is the shunt field current. IA is the armature current. Okay, this one is IA means armature current, and IF is the field current. Okay, EB is the back EMF, and VV is the brush voltage. So okay, so anyone apply, wait a second. Okay, so my first question from you guys, apply here the KBL in between armature, terminal voltage and armature current, and find out the VL voltage in terms of EB. Apply the KBL, find out the BL equation. Anyone apply the KBL and KCL and find out the VL voltage. Anyone? बताओ भाई, KBL KCL तो पढ़ा होगा इन नेटवर्क थ्योरी. अप्लाई करो, गलत भी होगा तो मैं बताऊंगा. बोलो यार, 45 स्टूडेंट में एक भी नहीं बोल रहा. एनीवन? प्लीज रिस्पॉन्स.
IARA plus EB, sir.
IARA, 1 second. IARA and
Plus
IARA
EB.
plus EB. Good. Okay. Then any one term or also, actually voltage drop across the brushes now also. EB, what EB? This one EB, This equation is complete or not? This one. But also there na BB, because brushes are also drop the voltage across the brushes.
Yes, sir.
Okay, so but because of that ideal case, I have assumed that ki BB is 0 in across the brushes. Okay, so I have neglect this, so I have only terms of BL equal to IA RA plus BB. So here you can see here BL equal to EB plus IA RA plus BB. Okay, for ideal case BB equal to 0, so BL equal to EB plus IA RA. Okay. So second one, apply this KVL and KCL here and find out the BL in terms of field winding. Please go ahead, बताएं टर्मिनल वोल्टेज एंड फील्ड वाइंडिंग के बीच में रिलेशन कैसे निकलेगा BL का?
Sir, IF RF, sir.
Okay, good. BL equal to IF RF. Very good. So okay, fine. So here IF equal to BL upon RF. Is it fine?
Yes, sir.
So when you design the DC machine or any binding, means field binding, so when you design the field binding, after designing RF is constant or variable? Any machine. Just like for example transformer, when you design the transformer, or when you design in home, fan are also now binding are also there. So when you bounded the wire, so after that it is changeable or not, or it is fixed?
Constant.
Constant na. So
Yes,
RF is constant and VL also constant, because VL is the electrical supply. Okay, so you got the IF is constant na.
yes, sir.
So our field winding is the proportional of flux. If field winding current is constant, then flux is also constant na.
Yes, sir.
Okay, so phi is constant. So here you first you have to understand, in the DC shunt motor, the DC shunt motor is the flux constant in DC shunt motor. Okay, fine.
Yes, sir.
Okay. Okay, so here the first relation, phi is constant. One second. Phi is constant. Okay, and second one, from the equation, this equation, you got the IL equation. IA armature current. Okay, VL minus EV RA. ठीक है? Okay, so my second is RF is much greater than RA. Okay, second point you have to remember, RA. Clear? This is means 230 ohm. If you in terms RA is 0.1 ohm. like that. Why we are used, I told you earlier. So you have to remember this. RF is much greater than RA, means field winding resistance is much greater than armature winding resistance. Okay, clear? So my next question is, okay, when we design the armature binding, so induced EMF depending on the in these parameter phi and P Z upon 60. You know this equation? You know about this equation? क्यों? Back EMF, when we design the armature binding, the parameter also find out the formula. So depending on the flux, speed, pole, conductor, Z means conductor, 60 into A means parallel path. Okay, so flux is in DC machine, flux is constant now. Fine. Speed is variable or constant? बताओ भाई. हाँ, स्पीड छोड़ देते हैं अभी. ये बताओ पोल. एनीवन अबाउट द पोल? नो अबाउट द पोल? व्हाट इज पोल? पोल, you know magnetic pole, south pole and north pole.
Yes, sir.
Yes, sir.
Okay, so in south pole or north pole means when you design the machine, so it is fixed or not?
It is fixed, sir.
After the designing part, I just want to know, after the design, so pole is constant or not?
Yes, sir. Constant.
Constant. Okay, so pole is constant. Okay, so Z is the conductor, so Z conductor is constant or just take the example फैन ना. फैन को जब भरा जाता है, जब देखते होंगे उसमें बाइंडिंग की जाती है, बाइंडिंग भी, तो उसको भरने के बाद जो कॉइल लपेटते हैं ना वायर का, देखते होंगे उसको नंबर ऑफ जो वायर है, एक में कई सारे वायर लपेट देते हैं, है ना, देखते हो. तो वो चीज को हम लोग कंडक्टर बोलते हैं. तो मल्टीपल और चीजें देखते होंगे आप, पूरे सर्कल में आप यूज करते होंगे उसको, है ना. ठीक है ना. अनदर एग्जांपल इज थ्री वायर लाइन, ट्रांसमिशन लाइन also there now. One line is many of wire are connected together, so this is called the conductor. So it is fixed or not? In the distribution na, actually in industrial area, or you can see in the places, the pole are three phases na, one phase, two phase, three, so three phase in the form of wire, lot of wire connected in single line, so this is called the conductor. Okay, so conductor are fixed na, actually you have to connect it in a line. So actually you don't to change the wire connection. Okay, it is fixed when we design. After the designing, conductor are fixed, so this part also the fixed. So this is the constant part. A means parallel path, how many connected in the circuit, this one parallel, This is also parallel. So this is two parallel. Actually, two lap winding in DC machine. One called a lap winding. Okay, and second one is a wave binding. This one is wave binding. Okay, when we talking about the lap binding, it is called the it similar to pole. Okay, when we use the two pole machine means two parallel paths are used. Okay, in wave binding a parallel path always fixed equal to 2. Okay, always fixed. However, you have to use for two pole machine, either four pole machine. It is fixed. Only two parallel paths are there. Okay, in lap binding it dependent on the pole. When we use two pole machine, so A equal to 2. When we used four pole machine, four pole means matlab P equal to 4, then A equal to also A also is 4. Okay, so A is also fixed because only dependent on the lap or wave. Okay, so here I have to finalized in proportionality. It is only dependent on the speed in DC shunt motor. Okay, other part is fixed. So EV is always proportional to N only. ठीक है ना? Actually flux is constant, P is constant, P Z is constant, A is constant, 60 is constant. So only dependent path is speed. Speed is variable. Okay. So, but in DC machine, actually this is about only DC shunt motor. DC shunt motor. Okay, DC shunt motor, but we generalized this form in DC machine. It is proportional to flux and speed. So one relation comes out, EB is proportional to phi and N. Flux, actually flux part is constant in the DC shunt motor, but in DC series motor it is dependent on the field winding, because field winding or armature winding are connected in series. Okay, so it is dependent on the winding. So here field winding is constant because EF upon RF BL upon RF is constant. So IF is constant. IF constant means flux is constant. So here only dependent on the speed. But generalized form, you have to remember this part. EB is proportional to the flux and speed. Fine. यहाँ तक clear है? So here we have first stage in DC shunt motor, flux is constant. Okay, second one, RF much greater than RA. Okay, third one, EB proportional to phi N. Actually, I have used only generalized way. So this is the relation. First one is flux constant. Second one, RF much greater than RA, means armature resistance, and EB proportional to phi into phi into speed. Okay, and so my second question from here, BL equal to EB plus IARA when we applied KBL in between armature binding and terminal voltage. So here IA equal to VL minus EB RA. Okay, okay. So in remember the point is also torque is proportional to IA. You have to remember also this part. Torque is proportional. I'm not actually I have covering speed control of DC motor. Actually, this part is used in the speed of control of DC shunt motor. So I have just told that torque is proportional to armature current. Okay, so first one is torque is proportional to armature current, EB proportional to N, RF much greater than to RA, and phi is proportional to RF. This is the part of DC shunt motor. Okay, so my next question is that At starting, okay, at starting, IA much higher. Why? Okay. Before
Because
we
sir,
asking
there
this
is no
question, actually, one second, one second.
back
Before we
EMF.
asking this question, I just want to know when we use the speed control of DC center, you use the 3-point starter. You know about the 3-point starter?
Yes, sir.
So why we are use the 3-point starter in the DC shunt motor?
Sir, because at start there is no back EMF, so IA will be very large. So avoid this, we use 3-point starter, sir.
No, this is good, but I just want to know why we at starting we not EMF is 0. Why?
Because sir, there is no rotation, so EB is equal to phi Z and P upon 60 and N is 0, so EB is equal
Yeah,
to 0.
exactly. When we start the motorcycle, na, so at starting position, speed is 0, na. EMF is dependent on the speed. I told you, na, speed EB is proportional to EB. EB is proportional to N. So, for example, when we start the motorcycle, so at starting position, speed is 0, na. Speed is 0, EB is 0. Okay, so EB is 0 means back EMF is 0. Back EMF is 0, so IA equal to VL upon RA. Okay, so RA, I told you na, RA is 0.1 and 0.2 ohm. So if we assume that RA is 0.1 ohm and VL supply is 220 volt lagbhag. Okay, 220 230, so it is approximate to 2200 ampere. So this is the IA is very high at starting, can damage the armature winding. Okay na. So how to reduce the armature current? At starting, we use the 3-point starter. So that starter provide the external resistance in the series armature binding, in connected with series armature binding, and increase the resistance across the armature binding. Then 3-point starter means 3-point starter provide the external resistance. Okay, connected with armature resistance. Okay, so overall resistance of the armature is Ra plus R external. Okay, so this is put in this equation. So in this equation, Ia equal to what? Ia equal to BL upon RA plus R external. Okay, so here denominator is higher part, na. Higher part can reduce the armature binding at a starting position. Okay, so you can see here how to minimize the current at a starting. Starter is used. Starter means extra resistance added in the armature of DC shunt motor to control the current at starting, only starting. Because we seen na, at starting armature current much higher can damage the armature binding, so we use only at starting. So starting resistance required only at time of starting. Okay, because when motor runs, speed increases and back EMF induced and armature current reduces. Clear na? After that we motor run na, so speed will increases means back EMF induced and armature current also reduces after the starting. Clear na? So 3-point starter used only at starting. Fine.
Yes, sir.
Okay, so this is the advantage. It can provide a constant speed for fixed load. Its advantage of DC shunt motor. Its speed can be predetermined for a type of load. It's provider. Actually, this is the theory classes you have to understand when you study the DC machine. Okay. So I have coming my aim. So my aim is speed control of DC shunt motor. Why we use the why we control the speed of DC shunt motor? बताओ भाई. So it is good now because we wanted to my machine is working very reliable or higher efficiency of my machine. Actually, you want to perform at 20 rpm unit of the speed, and it is if you not control the speed, it is working on 40 rpm. So it is not good now because heat losses or armature losses are there, so efficiency is down. So if we control the speed of the machine, it is very good for efficiency as well as life of the machine, longer life of the machine. So it is good now speed control of DC any machine. So it is so we control the speed of DC shunt motors. So what is the method of speed control of DC shunt motor? You know about the DC shunt motor method, how to control when you perform the experiment na online basis. Method बताओ, what is the method, how to control the speed? मेथड बताओ क्या करता है, मैं बताऊंगा.
सर आर्मेचर रेजिस्टेंस से और फील्ड रेजिस्टेंस.
Good. Actually you have seen na here, this is the part na this one. Actually I'm getting this part, one equation and second equation. So first one, so you have so this equation from that EV in generalized way, EV proportional to phi into n na. Okay, in terms of speed is proportional to EV upon phi. Fine. Okay, so in EB in terms of terminal voltage and armature resistance, this is the BL minus IARA. Okay na, in that equation I am just putting the EB value BL minus IARA na. So speed is proportional to BL minus IARA upon phi. Okay, so how to control the speed? Be controlled by using the flux and resistance. Okay na.
Yes sir.
So this is the part by using the field control and actually disturb the field field winding flux. When we disturb the flux, when we disturb the field winding, okay, when disturb the field winding, flux is the part of field winding na. So when we disturb the field winding, disturbing the flux and control the speed. Okay, so what RA is the armature winding resistance. So why when we disturb the armature winding, we disturb the armature current. Okay, armature current and control the speed. So this is the method we have to study armature current, armature resistance and field winding. Okay, so this is the method. So okay, so my so here is the this is the DC shunt motor equivalent circuit, I told you earlier, VL is the terminal voltage, IL is the line current, and divided actually. Why we are called the shunt motor? Because two windings are connected in parallel. So armature winding, armature resistance, and this is the back EMF connected with the field winding resistance. So that is notation of RF. Okay. So first method we control by using the field winding. Okay. So we disturb the field winding. So here is the diagram. So VL is the terminal voltage, IL current, and I am not disturb the armature winding. So here only similar RA is the armature resistance and EB is the back EMF. I am just adding the external resistance RXT and connected with series with field winding resistance. Okay, so we disturb the field winding. Huh? Okay.
Yes, sir.
So my okay, one second. Okay. Okay, my first question is apply the KVL KCL and find out the BL voltage in between armature winding and field winding. Sorry, armature winding and terminal voltage VL. Applied the KVL KCL. You सर्किट डायग्राम क्लियर है? थोड़ा सा इसका मेरा डायग्राम अच्छा नहीं है तो थोड़ा सा समझना पड़ेगा। ये आर्मेचर करंट है, ये फील्ड करंट है और ये एक्सटर्नल रेजिस्टेंस है, IF है। होल्ड अ सेकंड, मैं एक काम करता हूँ। ठीक है, अभी सही है, ठीक है। अभी बताओ, यहाँ पे ये IF2 बता देते हैं, IF2 है। ठीक है, ये वाली करंट जो है IF2 है। हाँ, अभी बताओ मुझे, इसमें KVL KCL अप्लाई करो और VL की वैल्यू बताओ। You applied the KVL in between our terminal and armature winding. So find out the BL. बताओ भाई।
Sir, IA2RA plus EB, sir.
IA2RA plus EB. Very good. Okay. So first equation this one. And IF2 बताओ। IF2
VL by RF plus R external, sir.
VL upon RF plus R external. Okay, so when we compare the original circuit or compare between IF1 and IF2, what is the conclusion? Or IF1 is greater than or less than?
Greater than, sir.
Great, always. Which one, IF1 or IF2?
One, sir.
One, always, na? Always, or some condition are there? Actually, IF1 is this one. IF1 PL upon RF. This one, na? So this condition for always or some condition are there? In that circuit, when we connected the external resistance, if external resistance some value, it is always less than in comparison of IF1. Equal condition when we are external is 0. So this is original circuit become. If we short circuit this part, so this is the originality, na, means this is the minimum value of R external. Okay, so this is the original circuit, no, of DC shunt motor.
Yes, sir.
So this is always be greater than less than as compared to IF1. So from that condition, what about the flux? What about the flux?
Decreases, sir.
Decreases. So IF2 decreases. Very good. Because IF is proportional to flux, na? Fine. And that from that relation, this is that relation. When IF is less, na, in that circuit, speed will increases or not? We control the speed by using the external resistance, and you either you have to told that we disturb the field winding when we connected the external resistance in field winding. We control the speed. Okay, so this speed is higher or less in original when we compare the original circuit. We assume that n is the rated value of original circuit. Okay, so in n2 means this speed, this circuit speed, n2 is much greater than or less than compared to rated?
Greater than, sir.
Greater. Always or less? Always.
Yes, sir.
Because flux is less, na? Flux is less, always. Oh, flux is less, then speed will increases. Okay, clear? So when we control the above the basis speed, means we wanted to control, means we wanted to if speed is rated speed is 1000 rpm. Okay, okay, and by using the field winding, we control the speed. Field winding, by field winding, the speed will become 1800. Okay. Okay, so this is the variable resistance. We use in physical mode the rheostat. Rheostat is the variable resistance, na? You know about the rheostat?
Yes, sir.
So we wanted to control in between 1000 and 1800. We use the field winding because we control by using the field resistance. Sorry, external resistance in connected with series in field winding. Okay, so we control that speed from 1000 rpm to 1800 rpm. Okay, it is fine, but we wanted to control in 800 rpm to 1000. It is possible from that method. It is possible. We wanted to control between 1800 rpm to 1000 rpm. It is possible by using the field winding. It is possible. My question. बताओ भाई.
Yes, sir.
It is possible. How?
To 1000 to 1800, na sir?
Yeah, actually, I just want to know. We control in between 800 rpm to 1000 rpm. How to control by using the field winding?
Sir, by varying the external resistance, sir. If we'll
So by
increase the
varying
external,
the external, actually, you can see here, na? Actually, you can see here. You can see here. Flux is always decreases. If you want to blow the rated speed, you flux is higher, na? Always higher. Actually,
sir, we are going from
this flux is
1000
higher
to
than speed.
1800 or 1000 to 800.
800 to 1000. 800 to 1000.
Oh, no, sir, then it is not possible by this.
It is not possible by using the field winding. So we use the armature resistance control. Okay. So this method for below the rated speed. When we use the above the rated speed, we use the field winding. We use the field winding method, and we wanted to control in between below the rated speed. We use the armature resistance control. Okay. So one more method, na, field armature resistance method. But question is that, so my question is, when we control these, actually here first we if decreases, if2 decreases. Okay, if2 decreases, then flux decreases, then you can you say na speed will increases. So it is possible to surge actually immediate change in the speed. It is possible when we, for example, you use na fan. When we use the switch on, the fan achieve the rated value after some time. You see na, in the home, when we switched on and see the fan, they achieve the rated value at some time, and you start the bike also. You in first gear, after taking some time to change the gear, and taking some more time for third gear and fourth gear, between some time na gap in between any gear you have to use in the motorbike. Actually be sensing that the first gear is achieve the rated value, then switch to the second gear, and after some time you sense that the second gear is achieve the rated speed, then move to the third gear. Okay now. So my question is that when we decrease the flux, how it is possible to instantaneous change in the speed? It is not possible now, or it is possible? You understood what I am saying? क्यों भाई? question is that IF in that case, IF R external is increases, IF2 decreases. Second one, flux is decreases, speed is not increases, instantaneously. Immediate change in the speed. So we decrease the back EMF. ओके ना, स्पीड को हम कभी भी इंक्रीज नहीं कर सकते एकदम से. एक्चुअली फ्लक्स जैसे ही डाउन हुआ उसको स्पीड कैसे बढ़ा देगा, है ना. तो उस मूवमेंट पे क्या होगा, वो बैक ईएमएफ को डिक्रीज कर देगा. फ्रॉम दैट रिलेशन you can see here flux is down, speed will not change immediately, so that reason we decrease the back EMF. Okay, understood or not? Understood? Flux decreases, speed will not change immediately, so we reduce the back EMF in that relation. ओके, ये पॉइंट क्लियर हो रहा है कि नहीं? हेलो, anyone responds me?
Yes, sir.
So we reduce the back EMF. Fine. So back EMF decreases, then back EMF decreases, then IA is decreases or increases? IA is increases now, because voltage drop decreases. Voltage drop decreases means armature current increases from that relation. Okay, this is the step by step procedure to change the speed or increase the speed in field control method. Okay, in field control method. Okay, so before we start in upcoming relation, I have to ask one question. In what is the difference between electrical quantity or mechanical quantity? For an example, when we switched on in the house, the light is immediately achieve the rated value, but fan is not. What is the difference between? लाइट एकदम से अपनी रेटेड वैल्यू को अचीव कर लेती है और ब्राइट हो जाती है, बट फैन थोड़ा समय लेता है रेटेड वैल्यू को अचीव करने में. ऐसा क्यों होता है? कोई बताएगा? एनीवन? Okay, because of the time constant. Time constant means in RL circuit, R and L. What is the time constant? Tau, notation tau. L by R ना? यही होता है. In RC circuit, RC, what is the time constant? बताओ भाई.
1 upon RC. 1 upon RC.
RC. ठीक है ना. तो मैकेनिकल क्वांटिटी मींस मोर टाइम constant, much time higher than electrical quantity. So that's why we use the we taking the some time in mechanical part fan is the mechanical part now, because B gives the fan give the mechanical output, and light LED bulb is give the electrical output. So electrical quantity time constant much lower than as compared to mechanical quantity. So this is the reason we mechanical output taking the some time to get the rated value. Okay, so this is the difference. Coming back to the third point, EB decreases, then IA increases from that relation. So then IA means relation between torque and armature current. This is the relation. So IA increases, then flux decreases, IA increases, flux decreases, then this part is increases. This one is the electrical torque, because IA is the term in the equation. IA is the electrical quantity now, current. Okay, so that's why this is the electrical torque. So this is the acceleration relation between the electrical torque and mechanical torque. Difference between both, it is called a TA. T means acceleration torque. TA, acceleration torque. So when we actually when start the any motor, machine will work at achieve the rated value. Fan any machine achieve the rated value at ETA equal to TM. When both torque are equal, then speed will constant, means achieve the rated value. Okay, at that time. So if in between electrical and mechanical torque difference in positive way, difference in positive, then speed will increases. Okay, if electrical torque and mechanical torque less than means negative, difference negative, then speed will decreases. So when we achieve the equal part, means electrical torque and mechanical torque are equal, then speed will achieve the rated value. So at that time, when talking about the original circuit, we assume that n is the rated value of the original circuit. Okay, so n is the rated value. At that speed, torque, electrical torque or mechanical torque are equal. Okay, at that time. But when we disturb by using the external resistance, electrical torque increases. Electrical torque increases means this part not disturbed. So electrical torque increases means TA will positive. Okay, TA will means acceleration torque positive, means TE is greater than TM. Okay, so TA positive means speed will increase. This is the condition after the 5 to 4 point. At this time speed will increases because acceleration torque will disturb at that time. Okay, so here speed will increases. Okay, then is 1 second. So speed will increases, then speed increases, flux down, EMF increases. Here EMF increases from that relation. Okay, so then EMF increases here, means voltage drop increases, IA decreases means IA decreases, flux decreases, flux decreases, then electrical torque. Which part decreases? जो इंक्रीज हो गया था, जो इलेक्ट्रिकल टॉर्क जो इंक्रीज हुआ था, वो पार्ट हमारा डिक्रीज होने लगा. दिस इज द इंक्रीजिंग पार्ट, विच वन इज डिक्रीज. सो हियर जब तक वो ये प्रोसीजर चलता रहेगा, जब तक ये चीज कांस्टेंट ना हो, तो वहां तक हमारी स्पीड बढ़ती रहेगी और स्पीड विल अचीव दी सम मींस n is 1000 rpm. Okay, and now get the by using the field n to 1800 rpm. सो 1800 आरपीएम इस स्पीड पर हमने इस सर्किट के लिए रेटेड वैल्यू अचीव कर ली कि N2 is the 1800 RPM. At that speed, acceleration torque is constant. Okay, so this point is the final point, means rated value of that circuit. So we control the speed from 1000 to 1800 RPM by using the field winding method. Okay, ये समझ में आ रहा है यहाँ तक?
Yes, sir.
So this is the method of field control, and another method is armature control. So in armature control method, okay, so in the next part, in armature, there's okay. This is RA, this is variable external resistance, this one EB, this is BL. Okay, IA, this one IF. Okay, so what is the value of IA in that circuit? In terms of BL, बताओ भाई। यहाँ पे
VL minus EP by RA.
BL minus
EP
EB.
by RA.
No.
RA plus R external.
Good. We disturb the armature binding. Okay na? This method by using the armature resistance control. Okay, and B similar RF is connected with across the armature binding, that is RF. Okay, so here IF is IF BL upon RF. Okay, okay, I am not disturb the field winding, I am just disturb the armature field binding connected with series external resistance in the armature binding. So this is the equation. Okay, so my first question is that this is increases na in equation first, EV equal to BL minus IA RA plus R external. Fine na? This is correct na? This equation correct or not? from equation
Yes.
first. So we increase the external resistance. External resistance means this voltage drop is increases, EB decreases or external resistance increases, then voltage drop increases, EB decreases. क्यों भाई? EB decreases ना, and EB and so from that relation, EB decreases, then speed decreases ना, क्यों?
Yes, sir.
So here we control the speed. Assume that for example 1800 rpm to 1000 rpm. 1000 rpm is the rated speed of the original circuit. We assume that. So we control. So it is possible for higher than that speed also. We assume means 1500 rpm. We control in between 800 rpm to 1500 rpm. It is possible. 800 rpm to 1500 rpm by this method, armature control. बताओ, इज इट पॉसिबल? देखो यहां से देखते हैं. So B, you can see here external, this voltage drop always increases when we compare the original circuit, because in original circuit drop only IA into RA, but here is drop IA RA plus R external. So voltage drop is higher now, so always decreases EB in comparison of original circuit. So EB is decreases always. Okay, EB or other than this EB2 means by using the armature resistance control EB2 that time, and EB is the original, so EB2 is always less than the EB, means EB, this is the new circuit, EB2 always less than EB, always. We can say that this, क्यों भाई ये कह सकते हैं EB2 always less than the EB. So EB2 less than EB, that means EB2 always decrease the speed as compared to its rated speed. Okay, so it is not possible to control the higher than the rated speeds, below the rated speed. Okay, by using the armature resistance control. But my question from that, it is possible to immediate decrease the speed of the DC shunt motor. It is not. So we change the speed step by step. That is my question to complete in the notebook to how to decrease the speed in the armature by using the armature resistance control with the reference of field winding control. ओके आपको ये मेथड दोबारा से देखना है कि कैसे स्पीड कंट्रोल होगी स्टेप बाय स्टेप से. हमने तो ये कह दिया कि यहाँ से स्पीड कंट्रोल हो जाएगी, बट आपको स्टेप से देखना. दिस इज माय क्वेश्चन फ्रॉम दैट मेथड. बी you have to find out from that equation from step by step, then decrease the speed. Okay, ये करके देखेंगे आप. हेलो क्यों भाई? So we conclude that relation by using the field method we control the above rated speed. Okay. By using the armature resistance control, we control the below rated speed. ओके, कोई डाउट हो तो पूछो। हेलो, बोलो।
Yes, sir.
ओके, तो आज के लिए इतना ही, हम लोग क्लोज करते हैं सेशन को। थैंक यू।
Thank you, sir.
Thank you.
Thank you.